So we're going to talk about functions, and I'll just quickly go through the learning goals so that you know exactly what you should be at by the end. You need to know a fair few definitions, so it's functions and relations, domain and range. We've talked about domain and range already a little bit. Sets, some set notation, etc. You should be able to use those definitions to work with functions, to classify groups and objects, and also to communicate effectively. And you need to also relate these definitions to your work in functions previously, linear and quadratic, and in the future. So when we do cubic, periodic, exponential, logarithmic, etc. We'll also talk briefly about something called hybrid functions. And as we build functions, you'll get the picture of hybrid functions. The big thing here is that the stuff I talk about today is going to relate to your assignment that you'll have early next term. So this is the beginning of some of the teaching for the assignment. So just be aware and prepared for that as well. And obviously there's the work you can do on that. So let's start with, I'm just going to talk through the definitions. You'll probably find that if you're going to try and write this down, you'll probably find it's hard to keep up. So I'd suggest maybe you grab the OneNote later in the lesson and do some paraphrasing of your own if you want to. There's some set notation here. This is not strictly important, but you do need to know a couple of things. So I might just highlight a few of the important things. Item 1, the set is a collection of things in mathematics. So set actually, I believe, is the word in the English language that has the most definitions, or maybe it's net, one of those ones. But set's right up there. But the mathematical definition is it's a group of things, a collection of things. You will use these curly brackets to refer to that group. So you put all the things in the group inside the curly brackets. If you use square brackets or those normal curved brackets, then you are referring to a domain or range typically. So you have to be careful about your notation. Anything that's in a set is called an element. So I might refer to this being an element of the set. And you have this symbol here, which is exist or does not exist, or is an element of or is not an element of. So you might use that. It's probably more of a Math C thing, but you may use that in your assignment. It won't really come up in exams or anything like that. You give sets names. There are obviously usually mathematical norms, and the norms here that you'd call sets, usually alphabetically in capitals, but usually with a capital letter. And you also have subsets. So I'll give some examples of that in a second. So that symbol there means it's a subset, which means you have a big set of things. And if all the elements of another little set are contained in the big set, then that is therefore a subset of that group. And so you see there's an example here. If B is a subset of A, then all the elements of B are also in A. And you have not a subset. So if there's an element in B that's not in A, then it's not a subset. So you have that symbol. And you'll see that a lot in maths, a symbol where you have a mathematical symbol. If you put a little line through it diagonally, it means not that thing. So the most common one is you have an equal sign. If you put a line through it, it means not equal to. So you've got that situation. And then we also have these two. So the curve, like the U shape and the upside down U shape. So the upside down U shape is the intersection. And so it's saying A and B. You'll see the A and B here, saying A and B. So things that are in both A and B. Whereas if you've got the U shape, that means A or B. So it's things that are in A or possibly in B or maybe in both. So you'll see those symbols for sets come up in probability quite a bit later this year. So expect to see that. And then you have this symbol here, which is also a probability-based symbol. A given B. Also A, the elements of A, yeah, because it's a backstroke. The elements of A which are not an element of B in this case. If it's a vertical stroke, it'll be A given B, but we'll talk about that more with probability. So the elements of A that aren't in B, and if I was to be really honest with you, item 9 is probably not going to be that important for your assignment or any work we do this year, but it is in that list. And then we have this point here, the null set, which is actually quite important mathematically. In terms of sets, the null set is like 0 is to numbers. So for a long time, mathematically, the number 0 didn't exist. People didn't count to 0, so it just wasn't a number they had. And then it was devised that 0 was an important number. You couldn't go from 1 to -1 in just one jump, so the 0 was put in that place. And the same thing here. Having a set of nothing is important to the mathematics of sets. Doesn't really seem that important by itself, though. So there's some definitions. So let me talk about some examples. So the first example here is a set of all numbers. So I was trying to zoom in, but that probably wasn't effective. So the set of all odd numbers can be written as, I'm calling it O, and it can be written as O equals curly brackets 1, 3, 5, 7, comma, dot, dot, dot. The set of all odd numbers has an infinite number of elements, so we can't write them all in the curly brackets. So you need to either set it up algebraically, or you need to set it up with some sort of pattern that's recurring. You can add those dot, dot, dot to show the pattern recurs. We all know what the odd numbers are anyway. You can also say that 1 is an element of O. 1 exists in the odd numbers because 1 exists in this set. You can also say that the set of 1 is a subset of O. So the set that contains 1 is a subset of 1, 3, 5, 7, etc., etc. And so that's a little bit of a tricky one, and it will come up in probability to an extent, but the difference between just the element 1 and the set that contains just the number 1, they're two different things. And obviously the set containing 3, 4, 5 is not a subset of O. 3 and 5 are in O, but 4 is not. So 3, 4, 5 is not a subset of O. So it's almost a logical thing as well. If you can get the notation right, the logic's pretty simple. It's not too demanding. So let's have another set, which I call F, and this set is the factors of 20, and you can see them there. So the factors of 20, you can say that F is not a subset of O, because F contains 4 even numbers that are not in this set of odd numbers. And O is also not a subset of F, so we have those two situations. The intersection of F and O, so when you have the U upside down, it's kind of like an A, just missing that middle stroke, so it's F and O. Think about what numbers are in F and O, that's what the intersection is. In this case, F and O are just 1 and 5. The numbers 1 and 5 are both factors of 20 and odd numbers. So that's the intersection. If, on the other hand, you're doing F or O, it would be every number that's contained in O or F, which means it would be every odd number plus the 4 even numbers contained in F. That would be F or O. And just quickly to show you how that looks in a Venn diagram. So the set of F, well, this is a set of F here, we'll say, and this is a set of O. And in F, we have these numbers, 2, 4, 10, and 20. We have 1 and 5. I've put 1 and 5 in that intersection component because 1 to 5 exist in the odd numbers as well. And over here in the odd numbers, we also have 3, 7, 9, and all the other ones. So I've put a dot, dot, dot to show there's heaps of other ones. And on the outside, so neither F or O, we have numbers such as 6 and 8 and 12 and 14, and also dot, dot, dot. So every even number that is not 2, 4, 10, or 20. And you've seen Venn diagrams before, so that should be hopefully reasonably trivial. So shooting down, does anyone have any questions on set notation at all? That's going to be a dull silence in the video, which is exciting. The number system, so that's probably the hardest thing, I think, that set notation. You might just see the set notation. You might never have to use it, but you might see it, so I need you to be aware of it. The number system, very quickly, if you're in Math C, you might be covering some of this, or you might have, or you will soon. So we have numbers that you are already aware of. We have the natural numbers, which sometimes denoted as n, like this. So that's on purple, which is not ideal. So n like that, just a funny looking n with a double stroke in the middle, in the diagonal. And the natural numbers are all the counting numbers, 1, 2, 3, 4, 5, 6, blah, 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 blah. And then we have J, which is, J represents the integers. And so all the integers are just every whole number, including the negatives and 0. So the natural numbers are a subset of the integers. All the natural numbers are in the integers, but there's some extra numbers in the integers. And then we have Q. Q is the rational numbers, any number that can be written as a fraction. So basically, any number that can be written as a decimal without rounding, or those decimals that you can write where you use the dots to show there's a repeated pattern. So those ones like a third, for example, which is 0.3 repeater. So any of those ones that can be written as a fraction are rational numbers. And then we have the irrational numbers, or the real numbers, which contain the rational numbers and the irrational numbers. So the irrational numbers are numbers like pi and e, which will be introduced to later in the year, and the perfect number, or the golden ratio, as well as the square root of 2, square root of 3, square root of 5, square root of any number that's not a square number, basically. They're all irrational numbers. So the natural numbers are a subset of the integers are a subset of the rationals are a subset of the natural numbers, and the irrationals are also a subset of the natural numbers, but there's that scale. So you might also see questions where you talk about this works, or this domain works for every number that exists in the integers. So instead of writing down -3, -2, -1, blah, 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 you might just say the domain is the integers. So when we get to domains and ranges, this notation might be handy and save you time and be a little bit more mathematically correct. This is the big one. This is the one that you probably can get questions on in the exam and that you will talk about a fair bit in your assignment. So this is quite important, the difference between functions and relations. But first of all, a relation is just basically something that connects two variables, anything that connects two variables. So a relation could be just an ordered pair, a coordinate. That's a relation. When x is 2, y is 7. That's a relationship between x and y in one singular case. Could be a series of coordinates. You might use that relation where there's a series of coordinates to build a trend line or a trend curve. A relation really has very few restrictions. So as long as there's something connecting, whether it's that the temperature in degrees Celsius is equal to whatever it is in Fahrenheit, relationship between those two variables as a function, or whether it's just coordinates, or whatever it is, that some sort of connection is a relation. Whereas on the other hand, a function has very, very specific rules, and you need to know about functions. They're the main ones. So I'm going to talk to you a bit about functions. A function is a relation for which every x value there is only one possible y value. Now it's not that complex, but it's a little bit complex to think about. It's hard to determine if a relation is a function. So I'll just be a second, Josh. So instead what we use is something called the vertical line test. And if you have the function already drawn out, you can do a really quick vertical line test. And I'll show you how that works now. If we have a look at A, B, and C here, and I want to determine if these relations between x and y are functions, I'll draw a vertical line on each of them. Somewhere, as long as it goes through the curve, would be ideal. And you can see that in the first case, A, it passes through 2 points on the graph. And because it passes through 2 points on the graph, that actually means that this is not a function. Because for one x value, this x value here, there are two y values, which technically means it's not a function. It doesn't pass the vertical line test. This one over here does. That's not a very vertical line, I know, but it only has one coordinate. For every vertical line I could draw on that cubic, there was only one coordinate for x and y where they meet. And the same over here. For every vertical line, there was only one coordinate. And in one case, if I draw a vertical line straight down the y-axis, there's no coordinates because that's an asymptote. So B and C are functions, whereas A is not a function. B is a really nice function. It's continuous. It does all this nice stuff. C is a discontinuous function, and we'll talk about that a bit later. And it's got a couple of funnier things going on, but it does pass the function test. It's a function because there is only one y value for every x. If you are on your graphics calculators or Desmos, neither of them will do relations. They will only do functions. So if you try and plot A, you put in the relation for A, it will actually only give you half a graph. Desmos will give you this half of the graph. It won't give you that. That will be gone. So you have to do other stuff to get the other part. It will only draw functions. So that's functions and relations. Josh, you had a question? Or good? Any other questions? Okay. This is really quick. There's some stuff in your textbook about this that I suggest you read over. But again, most students can get away without too much depth in this, but you might need to know the language. So the two middle ones are the harder ones, and I actually get this back to front all the time, so it's something you need to practice. A one-to-one function or a one-to-one relation is a function. So I'm in black again, so it is a function. And if it's one-to-one, it means for every x there's only one y, and for every y there's only one x. And I put here, think linear. Linear is that situation. If you go along a linear function, as for every x you choose, there's only one y value that works. For every y you choose, there's only one x value. If a function is one to many, it means that there are many y values to every x. So 1x to many y, which is why it's written as 1 to many. Now, if here I'm saying think a sideways quadratic like this one here, like A. If you think that sideways quadratic, you'll see that for every x value there are multiple y values, or maybe none. Some of the x values had no values, but for some of the x values there were multiple y values, which means it's 1 to many. It's 1 to many because for every y value there's only one x value. So that means it's 1 to many rather than many to many, which I'll get to. Many to 1 means there's many x values for one y value, and this is fine. This is a function. Think quadratic. Quadratic has only one y value for every x value, but if you pick a y value, there may be two x values for that y value. So that horizontal line test might pass through the curve twice. And that's fine. That can still be a function because y is the the dependent variable. And many to many means for every y value there's more than one x value potentially. For every x value there's more than one y value potentially. And I'm saying think circle. Circle has that situation. So 1 to 1 and many to 1 are both functions, whereas 1 to many and many to many are not functions. So you'll need to be aware of that as well. Domain and range, any questions on that 1 to many to many stuff? I can see some people are looking baffled and some people are looking bored, which is fine, I understand that. I feel like I've maybe made the writing too small. I hope it probably is too small. I might just fix that very quickly because I can. No, it's going to be a pain. Okay, so domain and range next. You've been using domains already. You've been working with domains with the trig stuff. So you should be pretty comfortable with them. But I'm going to introduce the idea of, oh, I see it's moved. I'm going to introduce the idea of a independent and dependent variable as well within our domain and range section. So put simply, the domain is the possible x values and the range is the possible y values. If you have a function or a relation and you're asked to outline the domain or range, you need to determine what are the possible x values, what are the possible y values. If, and this is something you may wish to write down, if you get an exam or an assignment question asks you to discuss limitations, domain and range are a really good place to start, particularly domain. You'll typically be limited to a certain domain. So if you're asked to discuss limitations in an exam, start by talking about the domain, and then you build to your limitations of your function or whatever other issues you have there. So keep that in mind. Put mathematically, the domain is the possible x values, which means it's the possible independent values. The x value is the independent variable, and that means it's the possible input values. When you build a relation or a function, the x values are the ones that you input, and the y values are the ones that are output. They're the result. So when you're in primary school, I know that I've done this with younger classes before, you might talk about, early algebra, you might talk about a function machine and have somebody have a box or somebody dress it up as a function machine or a function monster, and you give them a number and they spit out some other number, and there's a function associated. X goes in, Y comes out. X is the x-axis, Y is the y-axis. X is the independent variable, Y is the dependent variable. X is the domain, Y is the range. So you've got that relationship. You can add that on now. And then just some examples here. The domain is typically restricted within the context, so keep an eye on that. And then the range is typically restricted because of the function. So the context will restrict the domain and then the function will restrict the range, maybe the context. So for example, if you're doing something like over time, you were recording something over time, typically time will start at 0. So you might have a domain, time is greater than or equal to 0. Or you might have a particular time where you stop. And so that happens. Or the context might give you a certain domain. And then what might happen is your range will be between 0 and m based on the function that you got. So here's an example. This function, which looks something like you might use for your assignment next term, has a domain of these possible values and a range of these possible values. Now, the function itself might not technically stop, which means you might just say that x is greater than or equal to 0, whereas y is between 0 and m. A lot of context, there won't be a domain. But we don't really say there's not a domain. What we say is the domain is all real numbers. So when you have that situation, you might just write that x exists in R. And remember that notation, R is all real numbers. And E means it's an element of. So you're outlining there that your domain could be any number. And that's the mathematical way of writing it. We're almost done. And then there's this little bit here I just need to bring up. I would typically use that. I'd kind of expect you to use that notation in your assignment. Most places will have that notation. The textbook talks about this notation, which is mathematically correct, so be aware of that. And just to go through that very quickly, if you use square brackets, you're saying from 1 to m, so that shouldn't be a 1, that should be a 0. From 0 to m, including 0 and m. So anywhere there's a square bracket means that number's included. If it's a curved bracket, it means that number's not included. So the second example down here, so if I went x is greater than 2, but not equal to, I have this. So I have a curved bracket there. So x is greater than 2. 2 is the lower boundary, but not included. And I don't know where that negatives come from either. Let's just make that a positive and pretend it never happened. It's greater than 2, so it goes from 2 to positive infinity. And infinity is included in this case, so I have that square bracket. So you might see that notation. Be aware of what that means. It comes up in your textbook, but it won't come up too much otherwise. And function notations, function notation, hybrid functions. Function notation, I'm pretty confident you will have all done, so it's not a big issue. If you haven't done it, it's really easy. Sometimes we typically write y equals x squared plus 6, which I've got here. That's a function. That's fine. That's how we usually write it when it's a relationship between x and y. We're drawing it on a graph. But if we're actually doing it as a function, we're saying I want to put some numbers in and work out what the output is. Sometimes you might write it as f of x equals x squared plus 6. So there's a function of x is equal to x squared plus 6, which means to work out the output value, I get the input value, I square it, and I add 6. It's like a recipe. It's telling you what to do. That's what that function of x is. And if you have a function of x, it's really nice notation. You can write down f of x equals x squared plus 6, which means f of 1 equals 1 squared plus 6. And f of 2 equals 2 squared plus 6. And f of 3 and f of negative 5 equals negative 5 squared plus 6, f of 100, etc. So you can actually, it's a nice way to notate your substitution of points in. You can use that function notation as well. It will come up. When we get into calculus, it will be important. When we get into some specific context, it will be important. So there's going to be a little bit of an expectation that you're making the right choices between y and f of x, but ultimately you can probably use both in most cases. And I've said here, don't mistake this for a new concept or idea. It's pretty much what you've been doing anyway. It's just a notational thing. And most of this is just notational. We can also do f of x algebraically. So we might evaluate, well, what happens to f of x if x is 3a? And then I get this. And I can simplify that down to 9a squared plus 6. So you can evaluate functions algebraically as well. And lastly, and this is something that is important for your assignment, is hybrid functions here. So this is a notational thing again. It's nothing overly complex. But a hybrid function is where you join two or more functions together. So where a situation demands that after a certain point in time, the situation changes for whatever reason. And there's a lot of context where that happens. So I've given an example. It's a pretty dull example. But I've said that where f of x is equal to x when x is greater than 0, and x squared when x is less than or equal to 0. Now, a little bit like when you do statistics and you have to make sure that your grouped frequency table, each number can go to one place and only one place. So you want it to be that 1 to 1. Here you'll notice I've done x is greater than 0, x is less than or equal to 0. So if I have x equals 0, I know which function I'm using. I know I'm using x squared. I've got to be careful I don't have a situation where 0 could go to 2 places or where 0 can't go to any place. So make sure that 0 is included but only in one place, or your boundaries are included but only in one place. This function looks like this. There's the function going down there, and there's the linear component there, and you'll notice here that they meet. So my last little bit for today is continuity and discontinuity. This hybrid function is continuous because it meets at a very specific point and carries on. It would be discontinuous if the function was something like f of x equals, that's an integral sign. Sorry, I'm really struggling to draw these curly brackets. There we go. F of x equals x squared for x is less than or equal to 0, and f of x equals 2 for x is greater than 0, then my function would look like this. It would be that quadratic component, and it would be x equals 2. And so it would be this green one here, and you see that this gap creates discontinuity. And so something's happened. The context might allow for that, but a lot of contexts won't. You can't just jump from one thing to another in an instant. Some financial context, you can. You get that step function situation. You might get a load of money at one point, but something like a traveling displacement velocity time context doesn't. You can't just, it might seem like it, I just really run really fast and I get to there, but I can't just go from here to there. That just doesn't happen. It does take some time. Doesn't matter how fast I am. So you can't have that discontinuity. So just be careful within the context that discontinuity doesn't exist. That's it. Any questions?